Good afternoon, good morning, and good evening, everyone. I am Pavlos Protopapas, and I'm the Scientific Program Director for the IACS. So it is a great pleasure to welcome and introduce Trevor today. Trevor received a liberal arts education from Macalester College in St. Paul. Then he did his PhD in Columbia University, and he was working in experimental studies of two-dimensional electron system. Then after that, he went to Japan, where he worked at the NTT, Basics Research for Laboratories. When he was there, at one point, he started doing machine learning, informatics research, exploiting machine learning tools to perform material research. After that, he came to Harvard as a postdoc, where he used machine learning tools to search for new 2D magnetic materials. And he worked at the Efthymios Kaxiras lab for 3 years. Then he became a professor, assistant professor at RPI. And recently he won the Career Award. Congratulations, Trevor. And his research interest involves using machine learning tools for material discovery and knowledge discovery too. So his talk today will be quantum material design using AI. Before I welcome Trevor, I just want to point out something. Still remember walking into the classroom and I see a student that I couldn't remember, sitting at the front, taking notes, asking a lot of questions. And that was Trevor auditing my classes. And then since then, he audited many classes and we have a lot of discussions. So it's a great pleasure to welcome him back, to see him be successful and hear him today. Let's welcome Trevor. Trevor, the floor is yours now.
Thank you, Pavlos, for the really nice introduction. It's really great to be back and looking forward sometime to being there in person to meet you all again. So my name is Trevor David Rhone, and the title of this talk is Quantum Material Design Using Artificial Intelligence. And this work is mostly work from my time as a postdoc in the group of Efthymios Kaxiras. I'd like to thank all the authors of the work, which are shown here, and point out especially Sean Desai, who is now an IACS scholar. And his contribution is really central to making all of this work a success. So the talk is at the intersection of material science and artificial intelligence. It combines condensed matter theory with condensed matter experiments in the form of digital data, alongside statistical tools and computational methods to do materials discovery. And not just material discovery, but also knowledge discovery. I'll use artificial intelligence and machine learning alongside data science a little bit interchangeably during the talk, but really they're related in this way, where data science, machine learning AI uses databases, data visualization, statistics, alongside some knowledge base to do discovery and understand more about data. So this talk isn't just about materials discovery; it's also about personal discovery. And I'll begin our journey together, my story, here in the main Maxwell Dworkin's auditorium, I think G115. Where I often listen to the lectures of Pavlos Protopapas, many IACS talks, and many seminars, many discussions are happening here. Also alongside the guidance of Professor Kaxiras, in addition to Bill Wilson, Philip Kim, and Dave Charbonneau, Vinny Manoharan, just to name a few people. Also, I had really many wonderful discussions and spent many hours speaking with and interacting with members in the Kaxiras group, in addition to all their friends and colleagues. So thank you so much. Looking forward to meeting you again in person sometime soon. So let's continue our journey together. Let's go back 1 year before my listening to lectures in this lecture hall. And I'm actually now in the group of Emir Jacobi, where I'm doing experiments on this material, chromium, germanium, telluride. So now I'm an experimentalist, and I'm doing ferromagnetic resonance measurements on CGT. But I have two problems with this. I'm having two hiccups that are preventing me from finding the first two-dimensional magnet ever. We hadn't been reported before, and I was working feverishly to get this done. But this resonance of the CDT was outside the range of my equipment, and so I couldn't measure this thing properly with my equipment. And also, chromium germanium telluride was air sensitive, and so I couldn't measure it very easily. I would take the machine, take the device out of the cryostat, and it'd quickly fall apart in air. So I had two problems. It wasn't chemically stable and didn't have the right properties. So I needed to find a 2D material that was magnetic and had the right properties I was looking for. And this was quite challenging. So I talked to Pablo Ferreira, who actually did some measurements on chromium triiodide at the time. But he said that chromium triiodide was even more chemically unstable. This is the only other layered 2D magnet that I knew of at the time. And so it was quite tough. So the goal was to find some new 2D material that was also magnetic. And there was nothing that we knew of at the time that would exist. Okay, so fast forward a year or two, and these papers were published, one on chromium germanium telluride, one on chromium triiodide. So my mission to be first didn't come true, unfortunately, but there were some really nice results that came out of this. So this view graph on the left shows MOC measurements, which essentially MOC measures magnetization, and it shows that there's a 2D map of chromium germanium telluride down to two monolayers, and that has signatures of magnetization below the Curie temperature. And on the right side, we have this hysteresis curve of this chromium triiodide showing down to one layer. We have a magnetic ordering. So before talking more about our main goal, which is to find more of these 2D materials, let's say a little bit about why they're interesting. So why do we care about magnetism in 2D, two-dimensional materials? Well, there are a few reasons. The first is that they exhibit this exciting emergent phenomena. And I'll say a little bit more about that in a bit. The idea is that a collection of particles can exhibit exciting, unfamiliar, surprising behavior that wouldn't you'd necessarily think about happening if you just look at a constituent of that collection of particles. Then there's Morgan-Wagner theorem, which suggests that 2D magnetic ordering shouldn't exist. So magnetic ordering in 2 dimensions shouldn't happen, but it does. And because it does, and that can be a little bit surprising, but there are a few reasons for that. Whenever something surprising happens in science, there's always interesting possibilities to find new phenomena that are emerging. There's also the applications side of things. These 2D magnetic materials could find potential use in data storage, and also perhaps be the materials that advance the new novel computing architectures of the future, such as those for topological quantum computing, where these materials could have topological order. But I won't talk much about that. I'll focus on the data storage aspects. So let's touch on this first point, emergent phenomena. And for this part of the discussion, I like always going back to this paper by P.W. Anderson titled More is Different. And the main idea for this paper is that a collection of particles is more than the sum of its constituent components. So let's take an electron, which is a bit like a tiny magnet, and let's make many electrons, so a collection of electrons. And it so happens under certain circumstances, the spins might order, and so you have ferromantic ordering happening. And the question is, under what circumstances can something like this happen? Under which circumstances can you find ferromantic ordering? And the goal is to use machine learning to find this emergent phenomena by having as input some properties of the constituent components. Now let's segue into talking about the data storage applications. And for that, I'll show this graph that I borrowed from IBM research. And this shows how materials advances drove technological innovation over the years. And this is for magnetic random access memory, or MRAM. And the idea is that in the 70s, these magnetic tunnel junctions were discovered. This enabled one to encode zeros and ones, these bits in continuous memory, by having spins either aligned or anti-aligned in this heterostructure. Now, fast forward 30 years, these materials are now more efficient. There are advances in materials which enable the read-write speeds to be faster and the energy efficiency to improve. But this took over 30 years to happen. And the idea is that by having some framework, which isn't the traditional framework of experiments or first principles calculations, one can hope to try to speed this process up. And where does 2D materials fit in? Well, as you thin these materials down and down, further and further, in the ultimate limit is the atomic limit, of course. And if you have a 2D material that's magnetic, you can potentially have a computer that is really tiny, really energy efficient, and has really fast read-write speeds. So now I'll introduce an outline to the talk. I first talked about the motivation. I did that already. And next, I'll talk about the challenges for the materials discovery. And then I'll segue into materials informatics. And for materials discovery, I'll talk about what materials informatics is. I'll define it a little bit later on in some more detail. Then we'll apply this materials informatics machinery to look at 2D magnetic materials in particular. Okay, so now for the challenges. The main point is that materials search space is huge. Let's put this into some context. So let's take a popular database, the IACS, the Inorganic Crystal Structure Database. There are over 200,000 entries in that database. Now let's look at the AFO, which is a database comprising first principles quantum calculations. That has over 3 million entries. And if we take the Chemical Abstract Service, which is just a collection of all the chemical compounds and molecules and crystal structures that were reported in literature, that is much bigger. It's 49 million. But if you ask some folks, they estimate the total number of potential materials candidates in nature to be something enormously huge, like 10 to the 100. To give an idea of how large this number is, let's compare it to the size of the universe, or the age of the universe, rather. Where the age of the universe is relatively small. It's only 4 times 10 to the 17 seconds. And so if you happen to be around at the beginning of the universe, I had a really nice lab with a really powerful equipment or a powerful supercomputer, and each material took you 1 second to calculate and get its properties, you would still wouldn't be done. Of course, in reality, first principles calculations are expensive and slow, or can be slow, and experiments are even more expensive and even slower. And so this problem of trying to find a material of interest and scanning through all possible materials candidates is a really challenging or seemingly impossible task. So again, our goal is to focus on finding new 2D materials and better yet, 2D magnetic materials. And the main approach I like to take is this data-driven approach. So not something that is traditional, not first principle simulations or experiments. So what does that entail? So let's consider graphene, which is a single atomic layer of carbon atoms, and other materials like MS2, which are other classes of 2D materials which have different properties, and black phosphorus, for instance. Can we, without doing calculations or experiments, understand that graphene is conductive, MOS2 is insulating, and black phosphorus is not that chemically stable? In addition, can we ask some scheme to tell us chromium triiodide is magnetic, and chromium germanium telluride is magnetic or not? And this data-driven scheme, I'll like to propose and ask to see if this can work for a problem is this one I'm calling materials informatics. And the goal for materials informatics is to do 2 things. It's twofold: to do materials discovery, and we'll focus on 2D magnetic materials, their chemical stability, and their magnetic order. So we like to know if they're ferromagnetic or not. We also like to know, will they fall apart if we make them in a lab? Okay, and we'll also try to understand how we can use these tools to learn something about a system, how the system behaves, and why do their properties emerge as they do. Okay, so let's start with what is materials informatics. And it's a combination of material science and artificial intelligence, where the idea is that artificial intelligence, or AI, or machine learning, approximates some function f of x, which takes some inputs which are easily attainable. These could be the atomic properties of the periodic table of elements and attempts to predict some material property, which is difficult to calculate or hard to measure, such as the magnetic moment. And again, the AI is used to approximate this function f of x. And this is I highlight a non-traditional approach to studying magnetism in 2D materials. Okay, so now let's talk about why we like to use materials informatics. So I've hinted at this before, and the idea is the source space is huge, and we want to have some way of quickly evaluating materials properties in this huge materials or chemical space. And typically functions, to evaluate them, it's very, very quick. So you take a linear model mx plus c, you know what m is, you know what c is, you can input x and you get y very quickly. This takes you milliseconds or faster on a laptop. So the goal is to build some function which does this and can be evaluated really quickly. Now, there's another thing hidden in the parameter space here. Now, notice that I have x1, x2 through xn. So this takes n number of inputs, where n can go large. So we can say that the descriptor space or the input space is n-dimensional and can be high-dimensional n-dimensional space. And the key point here is that humans have a tough time recognizing patterns in high-dimensional space, but machines don't. Machines don't really care how many dimensions of space are. So let's put this into some context, and let's ask ourselves, can we perceive things in 0 dimensions? So this is like take a number, and you can see how a number varies. That's pretty straightforward. Let's ask ourselves, can we perceive things in 1D? And yeah, we can see a row of numbers or a list of numbers and see how those numbers vary. No problem. What about 2D? Well, 2D is easy, right? You're looking at a piece of paper all the time and understanding the scribbles on it, or the graphs plotted on that 2D surface. And 3D is also not bad. You can take your eyes from the laptop for a few moments, look around, and perceive 3-dimensional space fairly easily. But what about a 4th-dimensional hypercube? It's more challenging to kind of decipher. And what about a 100-dimensional space? I think that's pretty much impossible for human perception, but it's no problem for machines to search for patterns that are hidden in this high-dimensional space. So that's a key advantage of using AI or machine learning to tackle these problems. Okay, next up, our journey continues, but gets maybe more interested, more lighthearted. So for this part of the journey, we'll be going far back in time, not just a few years ago, and far across different part of space. So for this part, I'd like you to humor me for a few moments and close your eyes and take a deep breath in and out, and go back in time and space and end up, open your eyes, in ancient Greece. And now you're an alchemist living in ancient Greece, and you know about a few chemical elements. You know a few things about them. You know that they have a certain color, and you know their atomic number. You know about iron, hydrogen, oxygen, air, fire, water, earth, for instance. And because you're Greek and you're clever, you ask and you thirst for knowledge. You want to learn more about these chemical elements, and you ask yourself, well, what is a good descriptor to describe these chemical elements? And you think, well, it should be something like atomic number and not the color, for instance. Then you ask, well, what are the trends in these data and how can I find them? And again, because you're a clever Greek philosopher, you assort these atomic numbers in increasing order. That's your algorithm for learning more about the trends in these materials data. And if you do that, you find the following: hydrogen, helium, lithium, air, fire, water, earth, beryllium, carbon, and so on. You notice a trend. The pattern emerges. What is the pattern? Well, it's that the atomic number steps by 1 most of the time. And with this pattern in mind, you might decide that air, fire, water, earth seem a bit out of place. They're not really chemical elements. You might also find that there's something missing between number 6 and the number 8, which should be the number 7. And can anyone guess what that number 7 should be? It should be nitrogen. And by repeating this process, filling in the gaps using the pattern you recognize from the data, you can then complete the entire periodic table of elements. And then you notice something interesting kind of emerges from your analysis. that this space of chemical elements can be described by a two-dimensional descriptor space, which in this case is the column number and the row number. Well, this is a fun example, which you're familiar with. Everyone here has seen the periodic table. But really we want to apply these ideas to study something that's more complicated, to look at crystal structures and their structure property relationships. So let's take a 3D crystal structure, and the one shown here. This happens to be diamond, and often diamond has a clear color. This one is red, and there's a reason for that. So what is the reason? Let's take a look at this crystal structure over here. So diamond is a lattice of carbon atoms, okay? And these are the C's showed here at these points. Notice here there's an N for nitrogen, and also this V for vacancy. So this carbon lattice has a nitrogen vacancy defects, and these defects give diamond this red color. If you change the structure of the lattice, change the defect, you get a different color potentially out. So there's a structure property relationship, and we like to use the tools from before to try to understand what this relationship is, to make quantitative predictions. And as you can imagine, this because crystal structures are more complicated than just chemical elements, this space, descriptor space used to do this is going to be more than just two-dimensional. Moving into flat land, into a two-dimensional space, we can ask the question, if we know what a hexagonal lattice of carbon atoms looks like, and its properties, this is graphene. If we take a hexagonal lattice of instead boron and nitrogen, how do the properties change? And do they change? It actually turns out that graphene is conducting and boron nitride is insulating. And could we develop some scheme to quickly evaluate their properties without doing experiments or first principles calculations? Okay, so that's the big question. And let's segue into the framework that we'll use to try to address that question. And that is this materials informatics framework. So what does it entail? So we need first a lot of data, and then nice descriptors and statistical models. As everyone knows, the data exists on the cloud. It's a joke. And these days, lucky for materials physicists, data are accessible. Okay. Now we'll talk a little bit more about that in a second. And people are spending their careers developing good descriptors or mathematical representations of molecules and crystal structures that we can exploit for inputs to statistical models. A couple of examples of these are the Coulomb kernel and the bag of bonds representation, which is play on words for the bag of words representation. And data science tools exist that are easily available, such as scikit-learn and Google's TensorFlow. So let's talk a little bit about data for a second. Now, about 10 years ago, materials databases didn't really exist, at least ones that weren't easily accessible. And nowadays, you have Materials Project, which is a database of quantum physics calculations, alongside AFlow, which is similar. And these have, hundreds of thousands, if not millions, of entries that you can access. There's MontNavi, which is a database based in Japan. It's the National Institute for Materials Science. I actually worked at NIMS for a few months. And there's a C2DB, which is a database devoted solely for the study of 2D materials. That again is based on first principles calculations. And there's OQMD, Nomad, and also ICST, which is based on experiments. So data are accessible, and if one researcher wants to do some product in using artificial intelligence and machine learning and materials science, one doesn't need to go to scientific papers and copy paste numbers and build a table themselves. That's really very convenient. Also, descriptors exist. Descriptors are mathematical representations of materials, and they consist of things like atomic properties or some scheme to encode the crystal structure of a material or its molecular structure. An example of this is if you're studying, say, ionic compounds, you might notice that the elements in the ionic compound exist or are from different columns in the periodic table. So a good descriptor you might want to use is a column number. Okay. Of course, there are more sophisticated descriptors that we can talk about offline if you like. And there are also statistical models which people have built and packaged in, for instance, Python modules that one can call very easily. This one is familiar to you. It's just linear regression, which is a kind of machine learning. And this one is maybe unfamiliar to some of you, is one based on decision trees. And I'll go through this fun example for predicting whether or not to give somebody a credit card or not. It's just a silly example. So in this case, we have 3 descriptors: age, student status, and credit score grading rather. And to traverse this list, we ask, what is the person's age? If they happen to be young, we then ask, are they a student or not? If they're not a student, we don't give them a credit card. If they're a student, then we do give them a credit card. So this is a case describing classification. We can also tune this through regression problems, which I'll explain a little bit about later on. And the really great thing these days is that all these tools exist in the data science ecosystem, where you can store your data using MongoDB, transform it using Python, make models from your Python transform data using sklearn, and then visualize your nice results using matplotlib. Okay, this is really nice set of tools available for material scientists. So with these tools in mind, we can then segue into applying them to study a certain system. And the one we'll promise that we'll focus on is one for 2D magnetic materials. So let's talk about these chromium germanium telluride compounds again. So chromium germanium telluride is ferromagnetic, and this is a crystal structure. It has this A2B2X6 crystal structure, where the chromium sites are sitting at the A sites, the germanium is at the B site, and the tellurium is at the X. 3X is above the plane and below the plane. By the way, this plot just shows a unit cell, so some part of the crystal structure it extends in X and Y direction. If you take a top-down view, again, it extends in X and Y. You take a part of the crystal, and you see that the A sites form this hexagonal lattice, and it's decorated by B site in the center of that hexagon, and 3 tellurium atoms or X sites above, and 3 below the plane. Now, something interesting happens when you change the germanium site, the B site, to silicon. You find that the lattice becomes anti-ferromagnetic. This is really surprising for me because germanium and silicon are in the same column, and they're not magnetic atoms. But by changing germanium to silicon, you can change the magnetic order. So there's clearly the structured property relationship here. So chromium germanium telluride is a ferromagnet. All the spins are aligned, and chromium silicon telluride happens to be anti-ferromagnetic, where the spins are anti-aligned. So there's definitely a structure property relationship happening here. How much can we explore this structure property relationship? So what I decided to do was make different chemical substitutions at A, B, and X sites and see what their resulting magnetic properties were. So I took this A2B2X6 crystal structure, and I decorated the A, B, and X sites using different atoms from the transition metal. For the A sites and the group 4 and 6 for B sites, and group 6 for the X sites. If you decorate this lattice with all the possible combinations, you get about 10 to the 4 different candidates. I chose 200 of those to perform my first principles quantum calculations, and I looked at extracting a few properties: the formation energy, the magnetic order, and the magnetic moment. Okay, and it turns out that these 200 calculations took me about half a year on a supercomputer. So these can be relatively slow. To make clear the atomic substitutions, essentially every other A site was from the list chosen here of traditional metals. The B sites, the ones here, were combinations of silicon, germanium, and phosphorus, and the X sites, above and below the plane here, were either tellurium, selenium, or sulfur. In the periodic table, they're shown here. A site substitutions in this part of the periodic table. The B sites are here, and the X sites are here. So from these first principles calculations, we can get the magnetic moment. And the magnetic moment is parameterizing how strongly magnetic these materials are, or their magnetization. So let's look at the magnetic moment for different A2, B2, X6 structures. And that's shown here, where the vertical axis is the A side substitution, the B axis, the horizontal axis is the B side substitutions, and the panels are the different X sides. Now, for instance, this material here, it represents chromium 2, germanium 2, tellurium 6, chromium germanium telluride, and it has some magnetic moment somewhere around here. If you made a substitution of the A side to manganese, you get even larger magnetic moment. There's a darker purple color. And if you make some substitutions, the color becomes lighter, meaning that the magnetic moment is greatly reduced. If you look at these panels, you notice that there's a trend happening here. You can't quite quantify it, but there is some interesting pattern here. And our goal is to use machine learning model to see the hidden pattern in these data and exploit that pattern for quantitative predictions. We can also do a simple-minded kind of data analytics study of these materials. In particular, we can take their interatomic distances. So for instance, distance between A1, A2, A1 and X2, X1 and X2, and so on, and then plot that distance against the magnetic moment. What about the structure affects the magnetic moment? That's the key question here. So this plot here is showing an A1, X1 distance, and we're plotting that against the magnetic moment. We see for some special value for the magnetic moment, rather for the A1, X1 distance, that the magnetic moment mu tends to grow large. Okay, not so for large distances or tiny distances. If we plot the X1, X2 distance, something similar happens where we see a trend in the distances and the value for the mu. We can also do PCA, or principal component analysis, and find that if you plot the first principal component against mu, there's again some pattern here. And if we plot the first principal component against the second one, and then color each dot, each dot represents a crystal structure, by the way, we see that its magnetic moment is changing. So this analysis kind of tells us that there's something about the structure that affects the magnetic properties. And by the way, feel free to ask questions at any time, and I'll stop and try to answer them. And for those of you who've forgotten or would like to refresher at what PCA is, principal component analysis is this dimensionality reduction tool. And here I'm taking some toy data in this X1 and X2 coordinate space. And essentially the data you can see varies most along this direction. So we pick the first principal component to vary along that axis. So we rotate these axes such that the most variation happens along this new axis here, and the second most along this axis. And this works also in high dimensional space, 3 or more dimensions, where we see that most variation happens in this direction, and we just rotate our space so that we can capture this variation in the data. Okay, now we don't only care about whether the material is magnetic or not. We also care about making it and not having it fall apart in the lab. So we need to have these materials being chemically stable. And it turns out that formation energy is a good proxy for chemical stability. So we've also calculated formation energy for the materials, and we can do analysis on the formation energy and try to make machine learning predictions for that as well. So these are the formation energy data. Again, the panels or the X side substitutions, the vertical axis or the A side substitutions, and the horizontal axis or the B side substitutions. And the color now is formation energy, where the more negative number you are, the darker the squared, the more chemically stable you are. And there's a clear trend here, going from left to right in the first row of transitional metals, you decrease chemical stability. And if you go from the second row to the left, the second row from left to right, you also decrease chemical stability. And so again, I'd like to have a machine learning model learn this pattern and exploit the pattern for quantitative predictions. In order to do that, we need to describe each crystal structure in some way. And for that, we introduce this idea now of materials descriptors. Ideally, you want to have materials descriptors based on something that's easily calculated or already exists in a table. And for these, I've chosen atomic properties, a little p. And we build the property of the compound, large P, by taking either some mean or variants in the list of atomic properties for the A, B, and the X sites. There are other schemes for doing this, but this is one that I chose to do for this particular study. We do this, we find that we have 61 total descriptors. We may not use all of them, but we have those available for us for our study. So atomic properties examples include number of unpaired electrons, atomic radius, and so on. Okay, now that we have material descriptors in a data set, we can try to build a machine learning model. And the one I'll describe here is based on decision trees. This is a decision tree. And this one is in particular random forest that is based on these decision trees. So we have our inputs, for example, our atomic properties, number of spin up electrons, and so on. Our outputs, we want to predict, for instance, the magnetic moment. That's typically hard to calculate or to measure. And we divide our data into some training data, test data for testing whether the model is seemingly working well or not. And we have a scheme for calculating the loss function and reducing the loss by tuning the regions that we're looking at and the positions of the nodes. So this may be fairly kind of difficult to understand, but if you haven't seen random forest regression before, but visually it's actually not so bad. So let's look at that by taking this toy example. So now I'll present to you some toy data, and let's take some data using the function sine of x. And our goal here is to ask if we can learn the behavior of an underlying function using a random forest regression, in particular a decision tree. So here I'm plotting our sine of x data. I'm adding some noise, and I'm taking now a decision tree with just one node deep. And what is that mean? If the depth is 1, then we go to just these 2 nodes here. If the depth is 2, we go further down. If it's 3, we go further down, and so on. Okay, so depth 1, this is our like prediction. The model says for the left of 3, we have this value. The right of 3, we have this value. That's not very exciting. So let's go a little bit deeper. And then our model starts to a little bit better fit the model, underlying function sine of x. And if you go further, we find that it's getting to be not so bad. But if you go too deep, then it starts fitting to the noise, and we really don't want that. So our goal is to find some function approximation which understands underlying behavior without fitting to the noise. And so what we do next is talk a little bit more about the scheme for doing that before applying it to our data. So we take our materials data. These are now just, again, dummy toy data. The idea is we have some points. Let's say there are these 3 points and 6 points, and they take us, let's say, a month or some weeks to measure each point. So ideally, you want to have some scheme of quickly predicting a y given x, and we break that up into training data, test data to train a model, then compare a model with our unseen data. Okay, so let's apply this to our data set. Using a random forest, in addition to some other tools, we train a model to predict magnetic moment. And this is the result with the quantum calculations on the horizontal axis compared to the machine learning predictions of the magnetic moment on the vertical axis, with this dashed line being a guide to the eye, representing the perfect prediction line, with the circles being training data and the squares being test data. Now all the points fall a little bit close, reasonably close to the perfect prediction line, indicating that the model is performing pretty well. So we're pretty happy with this model. One other nice thing about random forest is that you can extract descriptor importances. This model, for instance, suggests that the mean number of unpaired electrons is the most important descriptors in this set of descriptors. And if you think about the physics of it, this is telling you that the spins on the chromium sides are playing an important role. And if you think about the physical meaning, this certainly makes sense. It's not telling you anything new, but it's definitely making sense. Also, the number of unpaired electrons very much makes sense for explaining magnetism. And there's this descriptor here, the chemical space bag of bonds, which I can talk about a little bit more if you like, but I won't mention it here. In some cases where you find a descriptor that was surprising, you're really pushing this knowledge discovery idea where you found a descriptor that matches highly to the predicting the model, but it was unexpected. And then the idea is you explored why that could be the case, and this helps you to find potentially something new and exciting. So now we want to think about chemical stability via the formation energy. And not only do we want to be able to find new magnetic materials, we also want them again to be made in the lab and to be chemically stable. And so we went through and predicted the results for the chemical formation energy for the random forest model, and also models including the kernel ridge regression model and neural networks. It turns out neural networks surprisingly has the best prediction accuracy. Typically, this doesn't happen for materials data because neural networks typically require a lot of data. They're data hungry because there are many coefficients that need to be tuned. And our data set comprises about 200 structures. So this is surprising, but for the formation energy result, it seems to work out pretty well. Okay, so now we've trained our machine learning model on 200 structures. So this took me 6 months. And I've told you that there are 10 to the 4 different candidates in entire A2, B2, X6 space. Now, I don't want to spend many years calculating all the structures. So what I like to do is use a machine learning model to predict the results for the entire space, and then pick the ones that are important to me, and then verify them with DFT and then later with experiments. So I'm showing some subset of the machine learning predictions for the magnetic moment here, and for the formation energy here, with the usual scheme of A side substitutions on the vertical axis, B side substitutions on the horizontal axis. So these are my machine learning predictions. There were really too many. There are over 4,000 in this particular case. So what I did was I did some screening approach. I picked those that have a large magnetic moment, and I picked this number, 5 Bohr megatons, which means its magnetization is large compared to chromium germanium telluride, and also has a chemical stability better than that of chromium germanium telluride. And if you sift through our DFT results and machine learning predictions, which were then verified by DFT, we have a set of structures which are candidates to have large magnetic moment and to be more chemically stable than chromium germanium telluride. So this is already a huge success, but you may be skeptical. Maybe you don't trust machine learning at all, or you don't trust DFT. Well, I have some good news for you. By taking these predictions, I was able to scan the literature without actually making these in the lab myself, scan the literature and find that there were some cases where there's a class of materials known as metal thiophosphates or metal phosphates, which I didn't know at the time of doing the work, but there are many thousands of papers studying these kind of materials going back to like over 100 years. And there are over 200 known compounds in the bulk. That is many layers. And none of these materials have been thinned down to one layer that I know of yet. So there's a lot of opportunity for exciting research to see if the predictions actually match the experiments. Notice that they have the same crystal structure that as the one that I'm studying. In addition, there's this chromium germanium telluride, which is mostly matching selenite, which is mostly matching one of my predictions. And the only report I found in literature of this was from someone's PhD thesis, which gives you the sense that this is really an up and coming field of research. So to summarize, we've identified these chemically stable 2D ferromagnets, and we've been able to tune their magnetic properties and chemical stability by making chemical substitutions. We were able to exploit machine learning to predict very quickly the magnetic properties and chemical stability for over 4,000 of compounds in this A2, B2, X6 crystal structure class. And this is a non-traditional approach to probing magnetism in 2D materials. So this stage seems to be successful, but earlier in the talk, I told you there are 10 to the 100 possible materials out there. If you focus just on 2D materials, this space is still fairly large. So let's explore that a little bit and see where we can use these tools. So we have still a chance to investigate other crystal structure classes, such as chromium triiodide, which we haven't talked about. There are also multi-layers to consider. For instance, if you take chromium triodide and you make 2 layers, the magnetic properties change. What is the impact of the layer number? You can also make chromium triodide, put it on top of another material, and the magnetic properties also drastically change. So there's some role for studying heterostacks or heterostructures as opposed to homostacks, where the stacks materials comprising the stack are the same. And there's also the impact of twisting. If you twist the 2 layers, for instance, bilayer, Professor Kaxiris, Bill Wilson, Professor Kim showed that the properties of these materials changed quite a bit. So if you considered other crystal structures, multi-layered heterostructures, you get about 10 to the 29 or 26 possible candidates. And if you include twisting, this number goes up even further. So there's really a huge space of materials to explore, with which we like to use AI to help us do that. It can be the guiding compass that helps us explore this material space. Now, even though this talk is coming to an end, our journey together, a journey of material space is really just beginning. And we're hoping that these tools can help us to do that. If you'd like more information, the majority of material I discussed in this talk, please visit this paper. And here's a QR code for ease of access. Thank you so much for your kind attention. Please, I'll take questions now if you have them.
Okay, I have a couple of questions, Trevor. Maybe we can go ahead.
Mm-hmm.
So one thing that, so you tried random forest and also you try neural networks. Is any potential here to do the inverse problem, start for the properties you want and then you go backwards? Have you tried that or?
Yeah, this is actually something from discussions with you I've been wanting to try, and so it's on the list of things to do, but I haven't gotten around doing it myself yet. But it's a very exciting idea to look at.
Okay, so
I have a question.
Go ahead. Thank you.
I was wondering how are you choosing the different input properties that you're using? Because of course there's so many different input properties you could choose from. Mm-hmm. How do you kind of make that selection?
Yeah, that's a great question. So in the beginning, I was a little naive when I just started doing this work, and I thought, well, I can just get anything that I have access to. So I would pick up all the properties in the chemical table, periodic table, via a Python package called Mendeley. And they have a really large list of properties that you can describe for chemical elements. And my first attempt at this was just to use all the properties and pass it to machine learning model, and and then I will claim success and go home happy. But it was a disaster. It didn't work at all. So then I found I really had to kind of combine my knowledge of physics with machine learning to be able to prove the result. So I thought carefully, what are the descriptors that really should work for describing magnetism? So I constrained a bit the descriptors, the space that I used, by using some of my knowledge of magnetism. Does that answer your question?
Yeah, I think it does. Although it seems like one of your examples was like some of the descriptors kind of surprised, or you could be surprised by the descriptors being important. So I guess I wonder, do you kind of do this by trial and error of saying like, oh, I'll include descriptors that I think will be important as well as some other maybe more random descriptors and see what comes up? Or because I assume you don't want to over constrain your model either.
That's right. Yeah. So it turned out in this particular case, all the descriptors I found were like not surprising. And the exciting part comes when you find a descriptor that is surprising. I didn't find that, unfortunately, but it could happen, in another study, perhaps in the future. There are also descriptors where you really focused on describing the crystal structure. So, for instance, there is this soap kernel. There's also the many-body tensor representation, and there is this work by blanking on the name of the person, but they're using crystal graph neural networks trying to describe materials, where they don't. Well, they encode the property by looking at the crystal structure and looking at given an atom embedded in the crystal structure, what does its neighboring environment look like? What do the neighbors look like? And they encode this in a very long vector to try to describe the crystal structure. this is another scheme for doing that, where it's often difficult to interpret what the scripture means. But they've shown for predicting things like information energy, it's really successful.
Trevor, thanks for the very nice talk. And I'm wondering if it is possible to incorporate some equations from physics in your machine learning model. Perhaps that can assist the learning. Is that possible, or have you done something like that?
I haven't done that, but I'm definitely thinking about it. Actually, using some of your ideas. I think it's really important aspect that I think the community is just starting to look at yet. Right now, when we're trying to build neural networks to predict properties of materials, but the space of coefficients is so large, it's difficult to constrain it. But how can someone, for instance, use the crystal structure, the crystal symmetry in the class of A, B, X lattices to constrain a network? This is something we're kind of actively, want to work on sometime this year. I'll probably ask you about that in the near future.
Okay, perfect. Thanks.
Okay, Trevor, I have one more for you. So you're predicting some properties of the material. Okay, so you have an R-square measure, but will it be possible or more interesting if for every prediction you have some distribution like confidence intervals or probability intervals, or have you tried any sort of uncertainty quantification here?
Oh, that's a good suggestion. I actually haven't thought about doing that yet.
Because especially if you go away from your coverage of your training coverage, expect that you're going to make more mistakes. But since we don't have material there to test it, we don't know how good our predictions is, right? So maybe something you thought about it or you want to extend to that is just give some, inference to your prediction, especially if that's going to be used by other people to search for some material, right?
Right. Yeah, that's a really great point. You like to know how likely it's going to be having the property you predict to have. Yeah, absolutely. I think we'll try to include it in the next round of research. So the next round involves trying to start from a relatively small database and predict a really huge space. We're not concerning it at all this time.
Yeah.
And having a way of saying, it could have this property, but this much confidence. That would be a nice feature to include.
And thank you, Trevor, for giving this wonderful talk to us. And hopefully we see you soon on campus again.
Looking forward to it. Thank you so much.
And by the way, congratulations for the award once more.
Thank you. I really appreciate it. Thanks so much, Pavlos.